Yeah, Professor, we'll start.
Yep.
Yeah.
Yeah.
Yeah. Good morning, all of you, and I welcome you all for the day 4 CAN course on hybrid renewable energy system and microgrids. Uh, yeah, today's lecture is on wind farms in microgrids. Thank you all in joining. I'm handing over to Professor Saad Nakalvi to deliver the lecture.
Thank you very much, Dr. Siva, and good morning, everyone. So we will continue our course today by looking into the wind energy. Let me share my screen. Okay, entire screen. Yeah, yes. All right, and then PowerPoint lecture number 3, and then slideshow. Is it clear?
Yeah, it is clear, Professor. We go to the display settings.
Display settings, and
Yeah,
that's
it's fine.
yeah. All right. I think as we mentioned just now, let me put the pen. Maybe. Okay. So today we will be discussing on the wind farms in microgrids. Because as we mentioned before, there are two main components very important in microgrids, which is solar and wind, and plus the storage and the diesel generators and other sources which can be also utilized. However, these two are very, very important, and both of them are weather dependent, and they can help actually maintain the power requirement in microgrid systems. So what we are going to look into today, we will look into quite a number of what I call topics, starting from the fundamentals of wind power. I think that's quite maybe common and known to everyone. And advantages and disadvantages, because any renewable energy systems have some pros and cons. Site selections, I think I have mentioned this before. And today we will go into more detail on these site selections for wind turbines, like we did site selections for solar, like we discussed it. Types of wind power plants, because there are a large number of wind power plants. Size of wind power plants, different sizes. Okay, the types of wind turbines, and then we look into the types of the generators used in wind turbines, wind conversion systems, because this power from the wind, it has to be gone through a conversion systems, and then the control, power plant control levels, maximum power point tracking again, but this time for wind farms. So also in because whenever you have the power profile of any systems that is non-linear, and then there are different operating points, so this MPPT becoming an important reactive power and rotor voltage control, okay, for double fed induction generators, and then the impact of wind plants on the power system performance, and then issues. Wind power forecasting also, it's a very important topic, wind forecasting, and the same that happened for what I call PV or solar forecasting, and then wind power protections, and then fault right-through operations. Okay. So large number of topics to be discussed. I hope we can finish them within the 3 hours allocated today. All right. So I think first one with the introduction to the wind. So I think it's very clear that actually the wind is the motion of the air. It's produced by the uneven heating and cooling of Earth's surface due to the sun. And as we know, since the Earth's surface is made of various land and water formations, so we have sea, water, land, air movements. Okay, and there are many factors actually. There are all two main factors are necessary to specify, which is wind speed and wind directions in any what you call wind, because in the, for example, if we remember, we talk about the solar PV systems. There are two main factors. Two main factors. There are other factors, but there are two main factors. I'm not sure you still remember or not. One is the solar irradiance, and the second one is the temperature. These are the two main in the PV systems. There are others, for example, the clearance, the dust, and the other factors which affect. But however, the two main is the irradiance and temperature. And then we have seen how the power curve changes with the respect to change in irradiance and in respect to change to what you call to temperature. For the same things for the wind, there are two main factors, okay, which is the wind speed and the wind directions. These are the two main what you call things. So how the wind is being generated, I think, as explained, as sun warms the earth, okay, the atmosphere warms up. So what happened is the movement of air, that's the warmer air goes up and the cooler air goes down because of density, and that's create these movements, okay, and then that's how the wind basically being generated, okay. Okay, and the wind how this wind generators or the wind power generators works, so actually it's converting this kinetic energy, okay, from the wind turbines, okay, and convert it into this mechanical power. We use windmills are used to for their mechanical powers, and then convert it from mechanical power to electrical power. So this is how it happens, and then goes to transformers to the what I call to the distribution systems, and then to the utilities. So that's how it happens actually. So that's how. Okay, why wind power? This is always the questions actually people ask. Why do we need this wind power? Okay, yes, wind power is needed because first one, it's renewable. Okay, and it's always like I always get this question: what is renewable? Because this is the biggest question actually. Many people don't. What does means renewable? Anyone knows here how we classify this source is renewable or not? Anyone want to try? Because this is always the question, because there are some resources a bit questionable. For example, hydro, is it renewable or not? So what does means renewable when we see this source is renewable? Anyone want to try?
I mean, which, if I understand correctly, this meaning is like whenever we use that resources, that can also be used. I mean, the next time. I mean, it is not that 100% we are wasting that, which becomes uh, not usable. Like in case of hydro, as you said, water, it is just used to run the turbine, but it is not that water energy is wasted. It can be further used in some different forms of energy. So same with the wind, and same with the solar. That's the reason we say renewable.
Okay, good. Anyone else wants to try? Okay, there are quite a number of definitions actually. One of them which I do like and I prefer to use, but as I say, this is my preference. And the definition says renewables are sources which are naturally created. Naturally created. What does it mean? Naturally created means doesn't involve a human being in this process. For example, wind. Do the wind human being involved in the creation of the wind? No. Solar, sun. Anyone can stop the sun from shining in every morning? No. So it's naturally created. That's number one. Number two, it can be, can be used for human benefits. Means we can convert it, because there are some resources which we cannot convert. So this renewable is naturally created, and repeatedly. And another one is repeatedly. Means, for example, every morning, every day, we use the sun today. Tomorrow there will be another day with the sun. So it is naturally and repeatedly created. Okay, and can be, harassed to be used by for human being. So this is I think that's the most accurate definition in my opinion, I have ever found. Because that's actually you apply. For example, the solar irradiance, yes, solar every day comes. Wind, yes. How about hydro? Hydro, it depends, because hydro in some cases is not naturally created. You need to build a large dams. So what's the ecosystem of that area? Like I mentioned I think last week about this Three Gorges Dam in China. More than 1 million people have to be reallocated. Thousands and millions of trees have to be chopped. Natural habitats, animals, and so on and so on. So it's not naturally, but when the sun shines, nothing will happen. When the wind blows, nothing will happen. So that's, I think, the definition. I think I found it, as I say, is the most accurate definition for renewable. It is naturally, repeatedly created and can be converted to or used for human being benefits. Okay, so that's why I think you apply this definition to any source, and then you can see it is renewable or not. Okay, so it's clean, as I said before. Recycled, I think, or it means can be reused. I think that the term means reused every day. Wind turbines can be connected almost anywhere. Okay, means can be found. Okay, existing farms, and one of the issues is a reduction of cost, transportation of cost of electricity from faraway power stations. So one of the good things about renewables, for example, wind, we can install it next to the load, and then we don't have to use the transmission lines. Okay, and then we don't use any water compared to, for example, hydro or even solar. Also, we need to clean, so we need the water, but the wind turbine does not. Okay. And then we don't have to use coals. Okay, minimum operating cost is quite minimum operating cost, which is quite good. Okay, and also it has a short payback time. Okay, so in terms of operating costs, means after you install, yes, the capital cost is very high. Okay, however, the operating cost is quite low. Lubrications and oiling and maybe small minor maintenance, compare. And the payback time is also quite reasonably and acceptable. Okay, and rapid source of power. Okay, sometimes they can provide a very fast response. There are also some issues. Okay, as I said before, researchers, whenever we introduce something, we introduce another issue, and that actually leads to continuous of research. So the issues of wind turbines, I think one of the major one is a noise. Okay, and this noise, it's what I call it's subjective. It depends. If you are in a noisy area, you may not notice it, but if you are in a very quiet area, then the noise level can be. And this noise level, the issue of this noise level will increase with the time. Means when the wind turbine gets older, so it gets noisier. Okay, so but there is always a new innovations, in these wind designs. The current one, because there are two issues in noise, and noise is due to few factors. One is due to the blades when they break the wind, and that's one. The other one is the mechanical noise inside the conversion. Maybe if there is because there are some wind turbines come with the gearbox, so that's actually noise within the gearbox, and also the wind of vibrations. Sometimes these wind farms actually wind turbines vibrate, so they create some noise. So there are actually a number of noise. But as I say, it depends on the surrounding environments. If you are in a very quiet area, even the leaves falls from the tree, you can hear it. But if you are in is a noisy area like cities, whatever, you know, you may many things happen, so you never notice actually, even they are very noisy. Okay. And sometimes it needs open space. That's also another issue, which is similar to the solar. So you need an open space. Means when you install this wind turbine, they need to, facing for example, facing the sea, or that we cannot have in front of them buildings or whatever, because they block things. So that's why most of them will be installed on hilly areas, okay, and maybe on the shore, facing the sea, or offshore, on the sea. So, but space actually it's a major problem for all renewables, because, for example, you want to install large PV panels, large solar wind farms, so the space is very important. Okay, the amount of power supply is inconsistent. Yeah, that's actually similar to the solar, because it's the variation in the weather patterns. Okay, high investment capital costs. As I said before, that's very expensive for all the. Yeah, and then this one also birds, flying to the wind turbines. That's actually an issue, especially this. Societies or these NGOs which protecting or defending the protection of birds, So, but there are always a new innovative ways. Actually, these wind turbines now, when they rotate, they create some noise, and that noise actually makes the bird don't fly to them. Visual impact, yeah. That's also, some people have a problem with seeing this rotating machine every day in front of their house. They don't like this. So wildlife, I think we have included including birds and other objects. And typically the lifespan, which is around 20 years. And this is almost three times the payback time. The payback time is around 6 to 7 years. But the lifespan of this is around 20 years. So actually, it's quite good. Okay. And that's why, as I say, the site selection, it's very important. And it helps mitigate many of those issues. For example, in terms of noise, space, okay, birds and so on, visual impact, even land use. Some lands are cheaper to use, So if the site selection is properly selected, actually we can mitigate some of these issues without without any investments. Okay, I think we start with the first point in wind, or wind farm or wind turbine installations, is the site selections. Okay, so the site selections, first one is must be having a high annual wind speed.
Sir, sorry to interrupt you.
Yes.
Can I ask you a question before we move to this section?
Yes. Yeah. Please.
Sir, as you mentioned, few negative points with respect to the wind turbine.
Yep.
I'm not sure. I have heard that because of the presence of wind turbine, virtually what we are doing, we are changing the direction of the wind flow, because definitely the natural flow of the wind, once it crosses through the turbine, definitely it will get changed, I can say. So some people, some NGO, like they, as you mentioned, like the threat to the birds and noise, they say that it might impact the ecosystem, the whole ecosystem. To what extent this is true as per you, sir?
Okay, I think yeah, it may have some impact. It may have some impact, but the impact is very, very small, because when you're talking about the wind farms, how big is the wind farm compared to the area? It's typically quite small. If you for example take India. India as a big, huge country, or maybe I don't know the land of India. Let me take Australia as an example because I know the size. Australia is around 7.5 million kilometers square of land. Okay. Let's take the how many wind farms are in Australia out of the 7.5 million kilometers square of land. Maybe if you count the whole wind farms that exist in Australia, does not represent even 0.001%. Okay, so the impact of wind directions or change due to the wind turbines will be almost negligible. Yes, there may be some impact on a localized area where when this wind farm are being installed. Yes, but it will not be. Yeah, because first one, the wind farm. Okay, when the wind blows, first one the wind blows, from zero, touching the surface, up to a few hundred meters, above the ground, right? Most of the wind farms will be located around 100, 120 meters. Means above that, there is no impact on the wind movements. Okay, so yeah, there is maybe some impact, but it's not really what I call as
It's not alarming, we can say.
yeah, it's not significant. I say this word. It's not significant. Okay, yeah, but as I say, even anything, anything we do now, it has an impact on the environment.
Exactly.
Yeah.
Nothing is 100%.
Yes, but now we need to compare. So do we want a wind turbine, or we want a gas power station, or oil power station, or a coal power station? So the impact of these two, you see, if you compare, it's almost negligible. So that's the trend. Okay. Any other questions?
Thank you, sir. Very clear, sir. Not from my side.
Thank you. Thank you very much. Okay, so site selection. Let's go to the next one, which is the site selection. I think that's, as I said before, site selection is very important. Okay, and all we measure it by always the annual wind speed. Okay, what is the average, annual speed? Because there are some areas which are very good in some seasons, during monsoon season for 1-2 months, and then no after that. Or this is not. We have to look into the annual, because this wind turbine, you have to work throughout the year. So, and if you ask what is the minimum wind speed that we should consider, that's actually quite a very important decision. What is the minimum wind speed? Okay, in the wind speed in the wind turbines has two what I call two limits. We call it the cut in and cut out speed. Cut in, which is the minimum wind speed that makes the turbine works. The same like the solar. Remember, I think we have shown you the solar, and we will show you this curve later. The solar, we have it have the number of sun days and the number of day what we call sunlight, and the effective solar that we can use. For example, we have 12 hours. Out of 12 hours, we may only have 6 or 7 hours of good sunshine that can be converted to power. The same thing like the wind. Also, wind blows doesn't mean at any speed. Usually we have the cut in and the cut out. Cut out is the very high. Means if we let the wind turbine turn, they will destroy it. So this is we call it cut out. And the cut in is the minimum. So typically most of the wind turbines require like between 5 to maybe 15 meter per second to operate. 5 to 15. Everything above 15, it can be harmful to the wind turbine. And then, but if it is like 20, there is some ways on how we can deal with this kind of situation. We will discuss this, the blade control, the orientations. Below 5, then it's considered very low. It means the wind turbine will not really, we don't have enough torque because to generate the power. But recently, in the last few years, this is what I call low-speed wind turbines, which can operate at 3 meters per second. So these are some innovations. But typically, most of the wind turbines usually between 5 to 15, that will be actually the best of the optimum what you call wind. Okay, no tall obstructions in front of the what you call of these wind turbines, because I think obstructions will create first one, they block the wind, plus they will create turbulence. Actually, that's actually things. Open plain or open shore. This is actually, like I mentioned just now, facing the sea on the hilly areas. Actually, that will be very good, and also very important near to the load center. That is actually, if we can install these kind of wind turbines near to the load centers, that actually can save a lot. Because as I said before, transmission lines usually account almost for 20% of losses in the grid systems. So if we are designing a microgrid, okay, so if we can locate the wind turbines next to the load where we are going to use, I think that will be the most optimum. Or if it is not near to the load center, can be near to the grid also, because sometimes, you need to connect to the grid, right? So you cannot install a wind turbines and you don't have the grid, or the grid is very far, so you need to do a grid extension. So very important. And later on, I think I will mention this in the forecasting. Because when we forecast, we don't forecast. Yes, we forecast, but we in the relation to two parameters, which is the load, which is close, which is good, or if it is grid connections, then it has to be near to the grid. Otherwise you have to need to also, this is if possible, need to the road transportation. Sometimes, because transporting these wind turbines, it's very, very, very costly and also very challenging. Because you imagine the blades. Some of the blades are 250 meters. How are you going to transport something of 200 meters or even 100 meters? I'm just okay. Don't forget about 200 meters. Talking about 150 meters, because now the current one is around 150 meters. How are you going to transfer something which is of a length of 100 or 150 meters? It's very, very challenging. So, and all of them come as one piece. They don't like mental, 2 meters, 3 meters, 5. No, it's coming as one piece. So this can be very challenging. Okay, so that's why transportation, because during the it's quite important. Okay, and as we know, as I mentioned just now, some mountains or gaps, mountain gaps actually can help to increase the wind speed, because I'm not sure. I think that the wind speed increases as we go higher. Okay, because less friction with the ground, less friction. So as we go a bit higher, the wind speed. That's why there is always, before we design the wind turbines, we calculate the wind speed at the reference height, and then what will happen if we increase the wind turbine by another 2 or 3 meters? How much wind speed we will get, and then how much power we will get. So that's actually okay, town centers are highly populated residential areas, usually not suitable. Okay, most of in populated residential areas or close, people will have always objections and these issues, and they have preferably not be a choice for this. Okay, and then also this is also very important, historical data. Okay. Very important, because sometimes we may have data which is for 1 year. 1 year can give you an indication of the wind speed annually, like I mentioned before in the first point. But what happened the previous years? What happened 5 years ago? What happened 10 years ago? What happened 20 years ago? If we have this data, actually, it would help us to really predict and select the right, site for the wind turbine. Okay, because 1 year data is the minimum, but 10 years, 20 years, 30 years, if you have like 50 years data of wind speed of a particular location, so actually you can almost 99% predict that actually this site is good or not for wind turbines. Okay. All right. I think yeah. Any questions so far? Anyone? Okay. So if no questions, we continue. The type, I think there are quite a number of microgrids wind turbines. Some of them, they are some utility scales, which is, most of them are can be offshore and land. In the good things about offshore, you have very smooth surface, so there is no frictions. So the wind speed is almost constant and almost good, and but there are other issues. For example, transportation of power from these offshore wind turbines to the land and so on. The marine life effects, the ships movements. So there are other issues. But as I say, one of the best locations usually especially for land or onshore, it's the hills. Most of this hills area usually is not occupied. It's not residential. It has a very good access, to the wind farms. And also, like I say before, you may have like this microgrid here when you have solar, and next to it you have wind turbines. Or like here, you can see this small community here. We have solar on the rooftop of these buildings, and then we have the wind turbines. So this is a community, community level or residential levels, microgrids. So it's quite works quite well with this. And then the sizes. Okay, so I think this is typically an expanding version and never stop. The small wind turbines can go up to 10 kilowatts in size. And they are quite relatively small. Between 1 to 13 meters or 15 meters diameters. Okay, and the height is also not very high, around 37 meters, and they can generate about 20,000 kilowatt hour of electricity per year, which is quite good for small home or even small community. And then we have typically the intermediate size, which is the 10 to 50 to 500 kilowatt in size. They are a bit larger, can go up to 30 meters in diameter of the blade. I'm talking about the blade. The heights can go up to 50 meters height, and they can give up to almost we call 600 megawatt hour of electricity per year. Okay, around 600 megawatt. 600 megawatt per year. It's quite good for especially if you put it in conjunction with in hybrid systems, solar or diesel generators for remote areas. So typically, this is a good, a good size for a small community. Okay, if it combined with storage, with the diesel and solar, actually can provide a good supply. And then we have the large wind turbines. Okay, but here I think this 6 here is outdated. So now I think we're talking about 15. The one in the market is already 15 megawatts, already commercialized. So we're talking about 500 kilowatt to 500 to 15 megawatts wind turbines. And as I said just now, it can go up to even 150 meters of diameters. And it generates typically, talking about 10 megawatt to 10 to 12 12 gigawatt hour of electricity per year. So it's a huge amount of electricity. Okay, but typically most of them for microgrids, usually we go either it is small or intermediate, because this is a utility scale wind turbines for application, and to help, like it's like a big power plant. Okay, But the combination of few, for example, 10 kilowatt, or combination of few of 15 or 20 kilowatts can form small, what I call systems. Okay, maybe we can have one or two questions, because we have almost 40 minutes now since we started. Any questions so far on this part before we move? Because that's we practice actually 30 minutes questions, 30-minute questions, and then 30 minutes. So at least we keep everyone, awake and maybe focus with us, because we are, virtually attending this. Yeah. Any questions, please? Or if you have in the chat box. Is there any questions in the chat box, Dr. Siva?
Sir, I have one question, sir.
Yeah, please.
You mentioned especially in case of offshore wind, we are seeing some inquiries from customers like very large size of the wind turbine. You already mentioned like 15 up to 14, 15 megawatt. Um, my question is little bit related to the power system study point of view. So especially what is happening when we use any standard tools like Dixalent or PSSE or ETAP as for doing the studies, we are finding very difficult because this very limited number of OEMs who are into this very big size of the wind turbine, and we are finding very difficult to get the some sort of data to do some feed study or so. So how to can you advise a little bit on this? How, if in absence of data, sufficient data, how we could
Okay. Maybe to end, if I understood the question correctly, you are asking about to model these large wind turbines, right?
Yeah.
Or you're talking about data. You're talking about the wind speed and wind direction data, or I'm not sure. Which part?
Not wind turbine, not wind data, especially the turbine data, sir. I mean to say inverter, wind turbine inverter data.
Yeah. I think recently, as I say, this is most recently the 15 megawatts, and even further, there are quite a number of them. So most of this recent one, unfortunately, very limited information about the data, especially the power conversion units, and because there's stiff competitions, between
Correct.
different companies, there. No one doesn't want to reveal actually the details. Yeah, because there is a lot of competition between companies. But I think if you one of the reliable sources is the Vestas. I think you know it, right? The company, which we produce actually quite good wind turbines. But now recently there is some Chinese made and Chinese companies. The best way is to get in communication, especially if you are like doing feasibility study, because I think maybe at your stage, maybe you're doing some feasibility study, right?
Yes.
Of installing these offshore wind turbines. Because now even here in Victoria, in Australia, actually there is a big plan of installing these offshore wind turbines, and we're looking into large wind farm, because large windmills actually, in terms of power density, is very high. And then even the cost, same like we talk about, remember we talked about the central inverters and the micro inverters. So when you have single wind turbines, actually the power density is very high, and then the cost will be lower compared to smaller wind turbines. Yeah.
Thank you.
Okay, good. Thank you. Any other questions?
Any questions?
Yeah, please. Any questions in the chat box?
No questions.
Yeah?
No questions are there in chat.
No questions. Okay, I think maybe we continue. If there's no questions, and please feel free to ask any questions anytime or at any point of the presentations, okay? Because as I said, it's quite a lengthy presentation, more than 60 slides, so we will have some, time to ask. Okay, I think all of you knows this. I think quite standards, the tower, and why I put this here, because I just want to show you the effect, for example, the tower height. Okay, what will be the optimum tower height? As I said before, as we increase the height of the tower, the wind speed become higher. Okay, so what will be the optimum height of the tower? And this is to be done in sensitivity analysis. What will be the optimum? Because, for example, if I have 7 meters per second at this height, if I increase the tower height to this height, okay, another maybe 3 meters or 4 meters, what will be the wind speed? If, for example, jump from 7 meters per second to 9 meters per second, so there is a difference of 2 meters per second. 2 meters per second, I put it in the power equation, and they found what is the amount of power that I can get, and what is the cost, and how much this power to be sold, and then what is the cost to increase 3 meters. And then we can calculate actually what will be the optimum height of the tower, because the height of the tower has a good relationship, very close relationship with the wind speed. Okay, so okay, I think that's what we call all right. And what you call the wind, what you call the towers actually has gone through a tremendous what you call developments, you know, from this to this to this to this to currently now we're using what you call these tubular steel towers, which are very strong, and you can go and inside and do, for example, you're going to climb up, you know, you can do maintenance, the wires running down and so on, all that, you know. So it goes through many developments. Okay, inside the nacelle, you know, of the wind turbines, you know, there are quite a common and very standards components. Okay, I think here we know this is the rotor, okay, which is the rotor part, and then we have the blades, okay, and what you can see here, we have something called the pitch. This is the pitch control. Pitch control, it's a very important component in wind turbine. The pitch control actually is adjusting the blades angle with the wind. So this actually has multiple objectives. For example, if you have a very low wind speed, you can adjust the pitch to have a maximum interaction between the wind and the blade, so it starts and it can run. If you have a wind which is very high, which cross the cut-out speed, remember that I told you? The different wind speed have different cut-out speed. Some of them 10, 15, 20, even 25 meters per second. So if the speed reach that level, then this pitch will be changed, all right, to reduce the interaction, or to reduce with the wind, so it doesn't rotate faster. And also because I think if you look into here, the wind blades actually are very close to the tower, you know. Okay, so if the wind speed is too high, this actually may result, because these wind blades are made of fiberglass. Remember, it's very light and very strong. But if the wind is too strong, okay, this may result actually of, you know, this will hit the tower and then destroy everything. Okay, so adjusting the angle, this angle here, okay, you know, make it, you know, the interaction with the wind less, the surface, you know, the surface interaction between wind and the blade less, so that may protect the wind blades and the wind turbines. Okay, so this is actually the pitch control. Also, there is a brake system. Okay, that's also to control if the wind speed is too high. So to protect this wind, so there is brake systems which can be applied also. So pitch first, and then followed by brake controls. And also we have the yaw drive. This is actually to move the wind turbine to the direction of the wind. Okay, so you can rotate the wind turbine to the right direction. So this is the system actually that we used then. And then after that, what we have after we have the low speed shaft. I think that's very small, because this is, we call it low speed shaft, because this is rotating at a very low speed. And in most of the systems we have what we call gearbox, and this gearbox is to increase the, because this low speed shaft, if connected directly to the generator, it will not generate the voltage and frequency that we need. Okay, so gearbox to generate then we have the high speed shaft here, and then the high speed shaft is connected to the generator, and then the generators is connected to the transformers and to the rectifiers, and then from the rectifiers goes to the inverters and then to the transformers. And as you can see here, we have sensors, which measures the wind speed and the wind direction, and this information will be given to this yaw control, and also will be controlling the pitch control, how much will be adjusted. So these are the different components. I think I hope I have explained it well, but it's quite standard. But it's important to understand actually what is happening inside the wind turbine. So later on, when we do the control part, you understand actually what we are referring to. All right. Okay, I think I have explained this already now. The different, measuring the wind speed, for example, transmit to the controllers, the gearbox, increase the speed of the things. The yaw drive is to run the wind to the wind directions, controllers. I think I have explained every one of this. Okay, I think that's the blade. I think we mentioned before. Blades are I think the most maybe most expensive components, inside the wind turbines. Okay, and because the materials they are made of, they are very light and also very strong. It's the same materials used to fabricate the airplanes. The wings of the airplanes. It's a fiberglass, so very light and very strong. Okay. There is always a question on what is the optimum number of wind blades that we should have, because we have wind turbines with single wind blade. We have 2, we have 3, sometimes we have 4. Okay, so the question is, what is the optimum number of wind blades? Like I said just now, the question is, what is the optimum height of the wind tower? And then we answer it, right? We said that actually the optimum height of the tower will be, it depends on how much wind speed we gain after we increase the height, and that's how much power produced, and this how much power produced, how much we sell it, and then we calculate the cost of the 3 meters increase in the height of the tower, and then we see is it feasible or it is economically feasible or not. Otherwise, we just keep it as it is. So the same thing applies to the wind blades. Okay, as I said, wind blades are very expensive. Okay, so for horizontal axis wind turbines, usually most of the time we see 3 wind blades are the most efficient. Okay, 2 wind blades don't require a hub. Okay, and sometimes, as I say, we even have single wind blade turbines, but here you need another weight to counterbalance. But they are for experiment, for research purposes. Okay, and sometimes we have more than 3 multiple wind turbines are generally used for water pumping because they have very high torque. Okay, and as the number of wind turbines increases, noise, wear, and cost increases, and the efficiency decreases. So these are the trade-off. But as I say, typically 3 wind blades are the most efficient and the most commonly used component inside the wind turbines. Okay, so yeah.
Sure. Other than research purpose or some sort of development, from industrial point of view, what's your experience on 4 blades or 2 blades? Because I have so far seen only 3. This is very, I mean, new information for me, to me.
You can Google it, and you can see even single wind turbine actually running on a single wind turbine, a single blade. Okay, but as I said, I think because there are two factors here we consider. Higher number of wind blades actually gives you higher torque even at a low speed. Okay, give you a higher torque even at low speed, because what happens when you're having because what we want actually, the blades, we want the blades to interact with the wind, right? Every wind that's coming in is interacted with the blade, right? So actually the what you call, the ideal is to have a solid, what you call one big blades, which that ensures that the interactions of the wind. But as you said, because when you have also a large number of blades, what will happen actually? The wick behind because there is a wind from the previous blade will interact with the next blade. So there should be enough space between the blades. That's why there are many factors actually in the selection of the number of blades, But as I say, economically, with the efficiency, is 3 blades are the optimum size, the optimum number. But you can go for 4. For 4, for sure, you have more power. But does that amount of power, okay, what you call recovered with the cost of the 4th blade? Okay, so this is the what you call the trade-offs that you have to weigh. So it's always a cost, because they are very costly, to construct this kind, especially for large wind. But for water pumping, usually very small in size, and we require what you call multiple plates, and less interaction, because when you have the winds blades close to each other, they will interact. The wind that pass through from one blade will interact with the other one. So there is a minimum distance should be between the blades. All right.
Got it. Got it. More blade means more power. That is one thing is clear. Now we have
Yes.
to look for the other aspects also, and then take a call.
Yep. So, but theoretically, that's the number, All right. So, okay, I think in terms of wind, there are different types of wind turbines. There are typically 2 of them, which is the horizontal axis. Okay, horizontal axis wind turbines, and also vertical axis wind turbines. So these are the 2 main types. However, the most commonly used we call wind turbines are the horizontal one, which we see everywhere. Also vertical. These are some vertical wind turbines. This is a real vertical wind turbine. Okay, so they are as not really commercially what you call viable yet, but there are a lot of research on these types of what you call vertical what you call wind turbines. So as I say, it's only for research purpose so far. It's not yet commercially viable yet. The most common one, which is we usually find and we use, they are the horizontal wind turbines. Okay, and some of them, they have the EO control system, like I say before, which adjusted the wind to the turbine to the wind directions. Okay, some of them are, we call them upwind, some of them are downwind. So, but most of the modern wind turbines usually use the upwind. So, so the wind, the wind will be from this direction, facing the wind blades. Okay, most of them. So these are the comparison between the horizontal and the vertical axis wind turbines. So major components, at the height, means quite high. Major components are on the ground. So this is actually the comparison, because when you see the gearbox, the generator, even sometimes the power electronics are all up, maybe 100 meters height, but for vertical are lower. The rotating speed is quite high, rotating speed quite low, maintenance quite high, maintenance quite low. This is as a comparison. Lifespan, longer lifespan, installation cost is high, maybe this is low. Okay, so there are some pros and cons. However, actually, as you see, economically, they are horizontal wind turbines are the best option so far. Yeah. Some we call it small wind turbines. Okay, which are can be installed on rooftop of buildings. So they are quite good. Maybe they can go up to 500 to 1 kilowatt system. Which is quite a rooftop of the buildings. They can provide some support. Okay, but as I see, very small in size. Okay, so more wind turbines. They are, more practical. Okay, and they use less energy, and also sometimes may difficult to improve. So that's why there are many new what you call looking into new innovative ways how to do these future wind turbines. Yeah, because the traditional one is a large one which is installed far away in the cities, but new ones actually will be very small, installed in the rooftop of the buildings, like we see in the photovoltaic systems. For example, the glass of the buildings is solar cells, because they can be transparent, semi-transparent. On the rooftop, the solar panels, and then on the rooftop there are also wind turbines, smaller wind turbines that can be used. Okay. In design specifications and the noise requirements for wind turbines, actually, there are international standards. I think maybe India also maybe might follow the same standards. So there are IEC 61401 and 2, 3, and 4, and 3 and 2. These are requirements this is for floating offshore, for offshore turbines, and then for small wind turbines, and then the general requirement. This is, I think, a good reference, especially for the industry people who are using this or working on this area to review these standards. They are very helpful and very useful for what are the requirements. Okay, and then let's look into the how these wind turbines works. Okay, the conventional, I have explained before, rotational mechanical energy to electrical energy performed by the generator. Okay, there are different types of generators that we use. Okay, so these different generators that we use, we have some of them, which is the most common one, the squirrel cage induction generators, which are very useful and also very efficient. Also, this is quite commonly used, which is the DFET, the double fed induction generators, also quite popular and heavily used in wind generation systems. And then also we have the synchronous generators. Okay, so we will discuss all those later, and then we see how they're being configured and then how they are being used. So these are the different types of systems that or the different types of energy conversion systems. Okay, let's look into take one by one, and then we will look to them. So if you look into this flow chart, wind energy conversion systems, we have the wind energy, okay, and then we have the variable speed wind turbines, and then we have fixed speed wind turbines. Okay, so if you are using a variable speed wind turbines, okay, indirect drive, which is with a gearbox, like I said just now. There are some wind turbines comes with a gearbox, some of them without a gearbox, gearless. Okay, so the indirect drive means it's not connected directly to the generator, so it comes with the gearbox. And then here we have quite a number of uh, of generators that can be used. Okay, including the squirrel cage induction generators, double fed inductions, and so on and so forth. We also have a direct drive, which is directly without what you call gearbox, and this is quite compact, and also there is less noise. Okay, and one of the most common one is the PMSG, the permanent synchronous generators, permanent magnet synchronous generators. So there is no gear, no rotor windings, no brushes, no rotor losses, and size and weight reduction. This is very, very important, and this is gaining a lot of attention now, because once the size becomes smaller, because we're talking about putting it at a height of 100, 150 meters height, so in terms of size is less, weight is less, losses, no brushes. Brushes means maintenance, and no gear means there is no noise, there is no lubrication requirements, and so on and so forth. So this is quite what I call very commonly used in modern wind turbines. All right, so defects are the currently this is the currently the workhorse for wind industry, very commonly used. Okay, defect typically about 30%. Okay, and it's also enable generator side active power control. This is also quite interesting for active power control and grid side reactive power control. So this is quite interesting, and that's why it's becoming very popular and widely used. Okay, and then the reduced capacity of the converter is less expensive and require less space. Okay, all right. So this is quite. That's why I say it's quite important. But as we mentioned just now, the PMSG, which is the permanent magnet generators, have higher efficiency and also higher power density compared to other wind generators. Yeah, I think also in the chart here we see the fixed speed turbines. Okay, and typically we use mostly is the squirrel cage induction generators. These are typical wind turbines that have been used. There are two of them. Can be either a single speed or a two-speed. Okay, so they can operate in these two modes. Okay, now let's look into what you call typical configurations of these wind turbines. Okay, so for a fixed speed wind turbines systems is shown in this figure, what you can see here. We have the rotor here, and then we have the gearbox, and then the squirrel cage induction generators, and then we have the soft starter. Okay, and this soft starter is it's required and to be used in this. And then after that we have the power factor correction, the compensator, and then the transformer, and then the grid. So it looks this is a single speed. Okay, so it's quite direct, means from the generator. Actually, the soft starter directly goes to the transformer. We have also two-speed, where the configuration is used two of the shelf generators, two of them. You can see here. The first one, one is the high speed, another one is the lower speed. Okay, so they can operate in two speeds, and then we have here the switch. Okay, switch between the either the low speed or high speed. And also, this is single using single shaft configurations. Also, sometimes we may have dual shaft configuration. Okay, so when we have dual shaft configuration, means the low speed and the high speed are in different shaft, but we still have the switch. Okay, which couple both generators. Okay. Variable speed induction generators. I think this one we talk about this one here. Now we are talking. We have looked into this one, the fixed speed, and then now we're moving to this, the variable speed wind turbines. Okay, under variable speed wind turbines. Okay, there are also a few options, or a number of them available in the market. Okay. One is the rotor induction generators, and these have an external rotor resistance for the control. We have the double fed induction generator, which, as I mentioned before, with very commonly used, and with reduced capacity power converters, so we have less power converters used. And then we have the squirrel cage induction generator. Okay, so look into the first one, which is the we call the winded rotor induction generator. Okay, winded rotor induction generators. So all of them I can see here using the gearbox, and we have the external variable rotor resistance. An additional converter here, and for the control. And then we have again the same thing, the soft starter, and the rest, the transformer and the grid. Okay, this is the same, like almost similar to the fixed speed wind generator, except it replaces what you call with the winded rotor induction generators. Okay, and here what we use here, we use a diode bridge. You can see here, this is a 3-phase diode bridge, and also an IGBT chopper for the external resistors, seen by the rotor. So this is typically things. And like we said before, the most commonly used is the double fed induction generators with the reduced power capacity of the converter. So what you can see here, we still have the gearbox, and then we have the defag here, and we have the power converters. Okay, so this power converters is very, very, very important. So that's actually makes this and this is becoming more commonly used, especially recently with the introduction of new semiconductor power devices. Okay, where we see the power capacity of these converters increases significantly. Right? So and the stator is connected to both the grid directly, as you can see here. The stator is connected to the grid, and then to the converter into the grid, and the rotor is connected to the grid via reduced capacity power converter. But as I say, recently we have, after this, we will see some of the converters which has full power. Means we're talking about 10 megawatts or 50 megawatts can be driven by these converters. Yeah, this is directly. This is a full capacity power converters. Means you can see here we have the gearbox, we have the generator, okay, single generators, and then the filter, and then you can see here this is the rectifier circuit. When we have here, we have a rectifier circuit. Okay, and then here is the inverter. Okay, so what does this mean? Means actually we're talking about, if we're having like megawatt level here, so this converter have to be of megawatt level. So there is a lot, maybe series parallel connections of these devices to achieve the power requirements. So there are two converters here, which is they are identical to each other. One is operating at a rectifier, another one is acting as an inverter. Okay. So They can handle up to only 0.7 megawatt here, but as I say, recently we have the silicon carbide devices and the what we call GaN devices, which can handle higher power and higher voltage and higher current ratings. Okay. Also, we can see also with this is with the full capacity, means all the power that generated from wind turbine passes through these power converters. Compared to this one, it's just a reduced capacity, only not all of it. But here is full. Also, we have with the full capacity power converters, and we use the MPC, 3-level MPC, neutral point clamp converters. Okay, and this is, as I say, is to help reduce the voltage stress and current stress on the switches. So we use multi levels, and we can go up to higher levels, higher number of levels, because through a higher number of levels, the voltage stress and the current stress on the switches will be significantly reduced. Okay, and that actually helps to increase the power further and further. Okay. Also with another topology with a full capacity power rectifier. Okay, and in this here is also the same. Okay, we use the current source. We use the current source rectifiers and using the current source converters instead of voltage source. Here we're using the voltage source inverters. You can see here using the voltage source inverter. This is a voltage source inverter, but here we're using the current source inverters. So these are different topologies which can be used. Okay. But most commonly is voltage source. Most of the topologies usually we use voltage source inverters, not the current source. All right. Let me. Go back to the chart here. Yeah. So we look into the variable speed. Okay. And we have seen a number of what we call indirect control. Indirect means with the gearbox. Most of them we have seen now. We have seen this, okay? And then we have seen all of this. So now we will move to the next one, okay? So let's, this one done, we finish this. We have this, finish this one. So these are different topologies, different topologies with different what we call configurations. Okay, so this is also still indirect, which is using what we call 2-level voltage source converter. Okay, and 3-level MPC. Okay, so the same. We have a gearbox here. We have a synchronous generators, and then connect to the grid. So the question is always asking actually which one is the best topology to use. Yeah, the best topology to use, especially here when you're having full power converter, is the less number of switches. When we have a multi-level, I know multi-levels is good, okay, but the number of components, the number of switches increases. When number of switches increases, so it is the complexity of the control increases. And in terms of reliability, it means the probability of failure increases. So that's why the 2-level voltage source converter usually are the main dominant converter in industry, because they use less switches. But what they do this modular components, converters. So in modular, so in case one spoil, they remove the whole module and then put a new module. So in terms of I call reliability, actually it's much better compared to multi-levels. However, multi-levels nowadays actually it's becoming also quite, especially the MMCs, the modular multi-level converters is becoming very attractive. Also, the configuration with also full capacity, back-to-back. Okay, we call it a back-to-back. We're having one on side a rectifier, another one is an inverter. Okay, and this is both of them are current source. Usually, this is we're talking about medium voltage between 3 to 4 kilovolts. With the full but back-to-back converters with the diode rectifiers and also multi-channel boost converters. Also, this is excuse me. What you have here, we have two converters or two topologies. One is the single channel, and the second one is the true channels. We can see the single channel here. We have from the synchronous generators, okay? And you can see here there is no gearbox, okay? So we have a three-phase diode rectifier, okay? And then we have a boost converter here. You can see this is a boost converter. And then we have the voltage source inverter or voltage source converter, and then we have the grid. This is, we call it a single channel. Also, we can have what you call double channel or dual channels. You can see here there are two converters, two channel boost converters here. This is just to increase the power of this converter. So these are the, because this here produces a rectifier, rectifies the output from the generator, but it does fluctuate, depends on the wind speed. Okay, so this DC-DC converter actually it's regulated DC bus here, DC voltage, and then the inverter, and then to the transformer, and then to the grid. Okay, so that's the objective of using this converter in between, this boost converter to boost the voltage to higher voltages. Also, configurations with diode rectifiers and DC-DC converters. Okay, so this is another topology. Okay, where we can see we use what we call a six-phase generator. Here we're using a six-phase generator. You can see here there are 6 phase, 3 here and 3-phase generators here, and then means here we need the 12 diodes for rectifications. And then we have 3 boost converters here, 3 multi, we call it the 3 channels, or we call it interleaved boost converters. And then after that, we have 3 here, then we have 2 parallel 3-phase inverters. You can see there are 3 parallel here. One, this is one, and this is the second one here. Okay, so these are 3 parallel inverters that are connected to the grid, you can see here directly we can connect to the grid because very high power. All right, I don't know much, another maybe 6 minutes, 7 minutes. Any questions so far? I think we didn't have any questions. Maybe any questions from the audience? Maybe I will stop sharing. We give like 5 minutes. We give 5 minutes maybe for questions or comment or any things, because I didn't hear much today, much questions compared to, maybe stop presenting. Yeah. So if you have any questions in the chat box or any chat box, there's no questions, any what I call oral questions so far?
Sir, I have one question.
Yeah, please.
Yeah, how about when there is a fault in the system, especially DFI works?
Sorry?
If there is a fault in the grid,
Yes.
yeah, is there any steps need to be taken in the wind generation?
Yep. Yeah. Yes. For sure. The same. Any grid connected systems, there is always a fault. Detections and fault. What you call isolation. So in wind turbines is the same like the PV. So these wind turbines should be able to detect if there is a fault. If there is a fault, which can be handled, means it doesn't, because most of these wind turbines actually they are protected because they have large transformers which isolate them actually from the grid. So the fault from the grid will not be transmitted to the wind turbines, for example, to the converter or to the power electronics components. But if the grid is severe, sometimes they have to disconnect, They have to operate on islanded mode, So, and then some of the wind turbines, they have what they call the dumping load, where sometimes they have a large amount of power that is generated and then cannot be absorbed by the grid. Then it will be dumped onto these dumping loads. That's also very, very important. And if you have single wind turbines, it may be not a big issue, but if you have a large wind turbines, wind farms, so that's actually the biggest challenge actually to control. All right.
Yeah.
Any other questions?
See, in the microgrid also the same thing, sir. We have to isolate within the fault.
Yes. Yeah. The microgrid is less of the issues. Microgrid, I think it's the wind because the size, the system is smaller. So what we have, we don't have I have not seen a microgrid with megawatt level wind turbines. Most of it is, for example, few kilowatts to 100 kilowatts, systems. So most of it is within the microgrid itself, and the fault is localized. So it will not affect, for example, when we see a fault in the large grids, is maybe due to transmission lines which has some problems, or maybe one of the generators goes off. But in microgrids, this issue will be less. And if it happens, it's localized. Means it is within a single microgrid, and this microgrid will be automatically, maybe it is a fault, then it will be isolated from the main grid. Or maybe, like we discussed last week, we have this interconnected microgrids where if, for example, assume one of the wind turbines is faulty, so the other microgrid will come and support this current microgrid. So that's the good things of having these interconnected microgrids, which helps each other in in self-healing capabilities.
Okay.
All right. Any other questions? I think it's too. I know it's too heavy. There are a lot of but there are a lot of configurations, but this is necessary. If you want to do this, you need to understand this. Unfortunately, there is no shortcuts for this, so we need to go through these topologies. But I think very important for you to understand there are three. There is what you call with the gearbox, without gearbox. With the gearbox, we have fixed and that things. Without fixed, we have variable speed, and then. Most of this, you can see large number of them, but in industry there are only the three main wind turbines: the double-fed induction, the permanent magnet synchronous generators, and then the squirrel cage magnet generators. That's it. So the rest, yes, there are some research and some work and some prototypes, but the commercially available are these three. That's it. And the most commonly now is the permanent magnet synchronous generators, which are very common because power density, efficiency, lightweight, and also what you call cost factors, and maintenance also as an issue. Okay, we will have more examples after this, maybe. I don't know, is it time now?
Yeah, time is.
Any other questions? Any questions so far? Or
Sir, one more question I have.
yeah, please.
When there is a fault in the grid,
Yeah.
our conventional generators, they definitely feed to the fault. What is the scenario with the wind turbine generators? Will that also feed to the fault, or how exactly?
Sorry. The generally feed to the fault. What?
Conventional generators, sir, conventional
Yes.
synchronous machines, they
Yes.
are the major contributor to the fault.
Yes, correct.
What about the wind turbine generators?
Yeah, as I said, on the wind turbines, if we have, like we've seen just now, there is a lot of control. For example, in terms of the wind speed, because that wind speed has a relationship to the power. But for example, sometimes we may have wind turbines which go faulty. Okay, so this is possible. So the most of these wind turbines have the capability either to connect or disconnect from the grid. So they be isolated from the grid, so because to reduce their impact. Okay. So similar to what I call to the what I call to the photovoltaics, so they can be operated on islanded mode, so to reduce the impact on the grid. But in terms of control, most of these wind turbines, they are very, very well advanced in controlling, for example, the amount of power that be injected to the grid and so on. And later on, we will see on the MPPT how they implement the MPPT in order to reduce increase the power and reduce the what you call the fluctuations on the power supply to the grid. Yeah.
Basically, sir, I was trying to understand from the point of view of designing the equipments, for example, like circuit breaker or switch gear. So we design for the maximum fault withstand capability. So in that, we consider all the sources which can fit to the fault. So definitely grid is the one, and synchronous machine, conventional synchronous machine is the second, I can say. Definitely that is also part of the grid that will fit to the fault. Coming to the, let us consider a switch gear where it is grid connected. So whenever there is any fault, there is a contribution from the grid. Okay. In addition to grid, do we also need to consider contribution from the wind turbines for the sizing of the equipment?
Yes.
For example, like
Yes.
Okay.
Yes. Yeah. Yes, we have to consider because the wind turbine is becoming a part of the grid now. Yes, for the sizing of these circuit breakers, you need to consider the wind. The wind generators. Yeah.
So irrespective of the type of wind turbine generator, it will be the same. Like if it is a synchronous wind turbine generator, definitely it will continuously feed. But if it is an induction generator, will it also contribute to the same level or it will not?
No. Yes. It differs. Depends on the type of the generator that you have on the, because there is one is continuously feeding, right? Like the. So yes, depends on the wind turbine. And this one, I think my suggestions is to refer to the, there is some standards, which we use, into the sizing of the circuit breakers for the fault. Yeah.
Okay.
I may share it with you. Maybe I have some documents. I will share it with you, or with Dr. Siva. He can share it with all the participants later on the sizing of the protection devices.
Thank you, sir. Thank you.
Thank you very much.
Thank you. Like any questions are there?
Any other
There
questions?
is no questions, means we'll close the session, Professor.
Okay.
Yeah, we'll come back after half an hour. We'll have
half an hour. Okay. Thank you. See you after half an hour. Thank you very much. Bye.
Thank you.